Hello and welcome to my YouTube channel. I welcome you all to another question answer session. And let me tell you what, this is getting really interesting. Every week, we're getting very interesting questions on different topics, and I'm sure it is helping students at undergraduate and graduate level. This week, we've got two questions, and in this session, we're going to answer them. So let's begin. Right, so the first question has been asked by Zahid, and he asks, what are the factors affecting the coupling constants, especially the heteronuclear coupling constants, because there's too much variation in the J values and etc. Now let's see what's coupling constant. Coupling constant is a constant value that is calculated in NMR spectroscopy. It may be homonuclear or it may be heteronuclear. But what coupling means? Coupling is the interaction of two nuclei, whether similar nuclei, for example, coupling between two protons, or different nuclei, for example, coupling between a carbon and a hydrogen. Now, these nuclei, when they are close to each other, for example, if the protons are geminal to each other or vicinal to each other, or if the carbon and hydrogen are directly attached to each other, they can sense each other, they can see each other, and they transfer information through their spins and through the bonded electrons as well. The extent of this interaction is calculated in hertz, and it is seen as a split signal in NMR. So whenever you see split signals in NMR spectrum, it is because of coupling of two nuclei. And the extent of splitting is calculated or determined in hertz, which is known as the coupling constant. Now, the coupling constant varies in different situations. Let's first talk about the homonuclear coupling. For example, the coupling between two protons. Coupling can be observed between geminal protons as well as vicinal protons. You may also see allelic coupling, that is a long range coupling, or you may also see meta coupling in case of aromatic rings, which is also a four bond coupling between two protons. Ortho coupling, that is three bond normal vicinal coupling, and geminal coupling is a two bond coupling. Now, when you think of these different protons, when they are geminal, vicinal, or allelic, the first thing that comes in mind is the dihedral angle. So, dihedral angle has a great role to play in the extent of splitting or the coupling between two nuclei. And if you remember, you might know about the Karplus curve that shows the variation of the coupling constant with dihedral angle. So it is minimum when the angle is 90 degrees, and it is maximum when it is 0 degrees or 180 degrees. So the first and the most important thing or factor that affects the coupling constant value is the dihedral angle. Another thing that greatly affects the coupling constant value is the substituents attached or present closer to these nuclei which are coupled to each other. So in a homonuclear coupling system like in proton-proton coupling, if there are electronegative substituents nearby, it will decrease the value of the coupling constant. But in case of heteronuclear coupling, like the coupling between carbon and hydrogen, the value increases because of the presence of electronegative substituents. Usually, the coupling between two protons, that is in the range of a maximum up to 15, 17 hertz, but it is more than 100 for coupling between carbon and hydrogen or carbon and fluorine, so that the value is more than 100 hertz. Another very important factor is the hybridization of the carbon atom. Like, for example, in heteronuclear coupling, the CH bond, the carbon and hydrogen, they couple to each other. If the carbon is sp3 hybridized, the S character is 25%, which means that this CH bond is slightly longer with lower S character, and so the coupling constant value is low. If the carbon is sp2 hybridized, we have about 33% of the S character, so the value is a little higher. For sp hybridized carbon, it is 50%, shorter the bond, and higher the coupling constant value, higher the interaction, stronger the interaction. Similarly, you can see that usually in strained rings, the coupling constant value is very high, and that also probably is um, attributed to the higher S character into that bond that goes outside the ring. So ring strain also has a role to play in the coupling constant values. So these are the different factors that you have to keep in mind while determining or predicting the coupling constant values for different systems. I hope your question is answered. Thank you so much for sending an interesting question. The second question has been asked by Anwar Ali, and it's about Blanc rule. So he wants to know about the Blanc's rule, what it means, and what is the outcome of this rule. So, Anwar, I'll take you to the screen to answer this question, and then we'll discuss it.
Okay, so let's see what Blanc's rule means. Blanc's rule states that if we have carboxylic acid, in fact, a dicarboxylic acid in which both the carboxylic acids are at position 1 and 4 or position 1 and 5, they will yield a cyclic anhydride when they are treated or dehydrated with with acetic anhydride or heated. Similarly, if the two carboxylic acids are at position 1 and 6, dehydration will yield cyclic ketones. So it's a generalized statement and it can be applied to a number of carboxylic acids. So let's see some examples. So for example, we have this dicarboxylic acid, and you can see that the two carboxylic acid functional groups are at position 1 and 4. So if you treat them with acetic anhydride, this will yield a cyclic anhydride, which will have the same number of carbon atoms as in the starting material. Similarly, if we have the two carboxylic acids at position 1 and 5, and you treat them or dehydrate them with acetic anhydride, it will lead to the formation of a cyclic anhydride, this time a 6-membered anhydride with 5 carbons. So initially we have 5 carbons in the dicarboxylic acid. Here too we have 5 carbons plus the 1 oxygen of the anhydride, so a 6-membered ring is formed. On the other hand, if the two carboxylic acid functional groups are at position 1 and 6 with respect to each other, and you treat them with acetic anhydride, this will lead to the formation of a cyclic ketone with 1 carbon less than the starting material. So we have 6 carbons here, and the cyclic ketone that will be formed will have 5 carbon atoms. The cyclopentanone will be the product. Let's discuss its mechanism. So for example, we have this dicarboxylic acid and we treat it with acetic anhydride. Let's see what the mechanism would be. Let me write it in a cis form just for convenience. If this is treated with acetic anhydride, in fact heated with acetic anhydride, it will attack one of the carbonyl groups an oxyanion will be formed, and when it collapses back, it will get rid of this acetate anion. Right, so what we have now is an ester like this, and then we have our second carboxylic acid. Now this carboxylic acid will attack this carbonyl here, forming an oxyanion, and when it collapses back, it will get rid of another acetate anion and closing the ring with this oxygen, forming a 5-membered cyclic anhydride. See, this becomes the carbonyl again, and here we too have a carbonyl group, so we have our anhydride as a result. So 2 acetic acid molecules are released as a result of heating this dicarboxylic acid with acetic anhydride. Right, let's see how the ketones are formed. Okay, so if we have these 2 dicarboxylic acid functional groups at position 1 and 6 with reference to each other, 1, 2, 3, 4, 5, and 6. Then upon heating with acetic anhydride, it will yield a 5-membered cyclic ketone. So you can see that the starting material has 1, 2, 3, 4, 5, and 6 carbons, and the end product has 5 carbons. That means that this reaction completes with the loss of a carbon dioxide molecule. Let's see how this happens. So again, we will draw them close to each other just for convenience. So when this reacts with acetic anhydride, in the same way as we saw in the previous reaction, it gets rid of an acetic acid molecule, forming this ester. And in the same way as we saw in the previous reaction, this carboxylic acid attacks here, getting rid of another acetic acid molecule, and so we have first the formation of an acid anhydride having 1, 2, 3, 4, 5, and 6 carbon atoms and 1 oxygen atom. So we have a 7-membered ring with an oxygen and 6 carbon atoms. Now what happens here is that this anhydride, it tautomerizes. It tautomerizes on one side, forming an enol like this. The lone pair of oxygen forms the carbonyl again, and these pi electrons, they in turn attack this carbon here, which forms an oxyanion, and upon collapsing back, it breaks this carbon oxygen bond. Right, so we have the opening of this ring, this CO bond is cleaved, but we have the formation of another ring, and now we have a new bond formed between this carbon and this carbon here. So we have 1, 2, 3, 4, 5 carbon ring is formed. Watch it closely. So this is the carbonyl, the ketone. Then we have a CH2, this one, another CH2, this one, then another CH2, this one, and then we have this CH, right? And it is attached to this carbonyl carbon. So why it is CH? Because it has something else attached here. That is a new carbonyl bond formed here, and this oxygen takes this proton and it forms this carboxylic acid. Right, so this carboxylic acid goes out of the ring, and under the same conditions it loses a molecule of carbon dioxide, forming cyclopentanol. So this is all about Blanc's rule, which is applied to dicarboxylic acids. If the 2 carboxylic acid groups are at 1 and 4, it will form an acid anhydride. If they are at 1 and 5, again the same result. But if they are at 1 and 6, we have a cyclic ketone with one carbon less that is removed in the form of carbon dioxide molecule.
Right, so these were the two questions that we have tried to answer, and I hope you guys are satisfied with the answers. For rest of the viewers, do send your questions on the email address given below. I'll be waiting for your questions. See you next Friday with new questions and new set of information. Thank you so much for watching. See you.